Let me know in chat if you are able to hear a lot of background noise. So I live just opposite to the school, and there is some function going on. So that's a little loud. Any background noise you all can hear? Okay, good, great. So we want to discuss a few things today. Still, uh, generic design of, I would say, mostly big data processing, and if possible, we'll do a HTAP database design. All right, so this is the primary thing we want to talk about today: accelerating the big data workload. Before I go forward, I want to have a quick poll. Type yes no in chat if you are aware how query processing works in general. Let me know so that I can think what to talk about, and then I can keep discussing other things. All right, so I got a big no from Ananya. Mostly no. Anybody who is familiar, type yes as well. MapReduce is a good primitive. Thank you. I will introduce MapReduce as well. All right. So we'll start with MapReduce. It's fine. We can start from there, and then we can see how far uh, we can go. Mostly, I want to focus on this. These are the topics which I usually I don't get time to dive deeper into my usual cohort, which I take. So that is why this experimental cohort. So let's see how far I can take this. So before we go forward and focus on the main topic of today, that is accelerating. What is the meaning of acceleration? Where are the places where acceleration comes into the picture? Let's talk about the heart of the uh, big data workload, or big data processing, distributed system compute, this related concept, and that is MapReduce. All right. So there is a very famous paper about MapReduce, very easy to read. I'll just pull it up to that. Written by Jeff Dean, of course. And I will share it as well so that you all can read whenever you have time. And somebody just drop this in. Um, there are currently no parts. Oh, sorry. Uh, everyone building up chat. Right. So the idea is that how do we come up with a programming model? How do we come up with a programming model and use that programming model to have two key functions? That is, so we have got map reduce, right? Map reduce. Obviously, map reduce is built on top of two important concepts. Any guesses? Map and reduce. All right. This is essentially a programming model. It is an important concept, programming model. There is a lot of work going on in the world today around programming models. Programming models is way different from design patterns. So programming model is not equal to design pattern. All right. Uh, Before I go forward, this is a good topic for breakout session. So Google it. What is a programming model? Along, whenever we will whenever we will be sent in the breakout room. But it is something which is very critical. Why? There are, as I had mentioned last time as well, the evolution of hardware and software is happening very rapidly. So a lot of the time we need we need completely new programming model to design things. There is this open source project named Resonate, or basically say Syncable, right? So they are also designing a programming model. So here is the talk. New programming model for the cloud. Basically, he's going to talk about that how designing modern distributed async await is going to be possible with only with a new programming model. So programming model is something which a lot of people are which a lot of people are thinking about. Hence, it makes sense to just think about programming models. The programming model is not equal to design pattern. Now, by the way, design pattern in itself seems a little overrated to me. But I think this is more from the Java side of things, which we keep. Um, so here is my thought. Let me know if you guys agree or disagree with me on this. Uh, Design patterns were created in order to write good, manageable code by corporates who used Java. And since Java got popular, really, really popular, the new programming languages which came, the existing programmers needed some mechanism to adopt it. And it was a good selling point if you just say that, hey, we have a design pattern that is very similar to we support the same design patterns what we have in Java. So it was easier for corporate to trust that hey, our programmers can adopt this because of design pattern or something. But yeah, I can be wrong. But I don't think design pattern make too much sense to me, especially with modern programming languages. Managing change in the real world makes sense to the business. Yeah, it's just that from so when in interviews as well, when people are saying, "Do you know what is factory pattern?" It's meaningless because it's just a pattern. It's not that if somebody doesn't know certain pattern, it is a game. Like it's a it is a deal breaker, right? It is something which is just it's not even a technical thing according to me. Um, just a way to write good Java, basically. Design patterns can be so. For example, a lot of times what I've seen is people have gone to adopt uh, the what is the design pattern where we have only one object. Uh,
Singleton.
Singleton, correct. So, see, a lot of the databases have singleton design pattern. All right. So most of the like interview ready design patterns which we keep hearing about, um, very less places. You will find very less opportunities going forward, especially with reducing now all of this is around systems. I don't know what happens in the web development world or application world. So in systems, the grammar footprint is reducing that heavily for any programming language that a lot of the design patterns which people keep talking. For example, Rust does not have a um, proper. A lot of the systems programming language don't support things like polymorphism, inheritance. These type of things out of the box. Like some few, it's not every programming language support everything. So in that type of a scenario, if you are getting smarter into systems, want to build a good systems team, which I believe that it's the skill for the coming years because we have all the AI and the massive saturation at the application level is evident, at least to me. So now there is a massive need for programmers who understand hardware and they can write good, efficient code. So there, this whole interview process and everything needs to change. Anyways, we can do the rant later on. So coming back to MapReduce, MapReduce is a programming model which is not a design pattern, and it is built on top of two primitives, that is map and reduce. Now, as they as you might guess, map maps something and reduces the map into smaller uh, subsets. So what will happen is, let's say I have got, I have to sort two files. First file, and first file has got 1.a. This can be a good assignment, by the way, if somebody is interested. 1.b, um, 3.b, and then I've got another file where which has, let's say, 3a, 1a, but no b. So there are multiple files like that. So now what I want to do is I want to have a good word counter implemented. Word counter which can count the number of times of um so basically which can sum the tuples with the right key. It's not a word counter, it's just a count, or rather a sum. I want to sum the tuples with the right key. So in order to do this, I need to first do a map. From this file, I would need to find all the, let's say, A's from this file, or rather from the map job, I want to find all the B's. Once I have mapped correctly, then I can simply do a reduce. So all the aggregate operations, let's say sum, count, these kind of things, max, min, whatever. All the aggregate operations are basically come into the reduce, and all the mapping side of things, let's say, or creation of these kind of tuples and everything, these things come under map. So this is a good programming model to solve a complicated problem. Let's say like sum the tuple with the right key in a massively distributed system which cannot fit on one computer. And there are a lot of um algorithms which use MapReduce. For example, a lot of distributed sort, if you see, distributed sort, these are usually implemented on top of MapReduce. Let me see if I have a implementation for distributed sort ready. I think I should have. If I have, I'll share it right away. I think it's not there, or I might have not pushed it. But anyways, you can find double check sort. I don't doesn't have anything. So in MapReduce's paper, you will find explanation about all these things like mapping, key value mapping, and reduction. But more than that, you will find the distributed sort thing somewhere. Mm, grep sort. Yeah. Here. So they are sorting a huge number of 1 terabyte of data, huge at that time when the paper was written. And they will tell you what was the performance improvement, how the distributed sort was used, and everything like that. It's a good paper. It's a good fundamental paper, which you all should read. Those who have not come across MapReduce. So with that as a base, we now understand what MapReduce is. Now let's go and let's try to see um, a generic query processing engine, and from there we'll see how does acceleration come into the picture. So now we will try to understand this. The uh, design of a big data, generic big data. Sorry, generic big data query processing. All right. So the normal flow of a query in your big data system is I'll tie how MapReduce comes into the picture here. A query can be select star, whatever. Select star is actually not a right way to do things, but just assume that that is the query. When a query comes, it gets parsed and everything. Um, let's say you have a AST now. The parsing is done. So we have a parser, and then we come to a point where we have a logical plan, optimized logical plan. Sorry, yes, logical planner, and then resolved logical plan, logical plan. Then I think it gets optimized, optimized logical plan. Then you have physical plan, physical plan. Then you have cost optimizer. Then you have a final physical plan. So mostly this is how any, I would say, modern query processing engine would work. So let's say a query comes where we have a query like select name, age from table. So I'll use ChatGPT to quickly generate a logical plan for me. So give me 1 second. Wait, logical plan for this query. Yeah. So this is the example of a logical plan which gets generated. I also update convert give an example of logical plan. So filter push down. This is another example, and its query plan is going to be interesting. All right. So this is the plan, and this plan, we are going to talk about this plan. All right. So we have got this query. What does the plan say to you? It looks very simple that I have to select name and age from table. I have to select name and age from the table. So the output is going to be name and age, right? And how will you get name and age? You will get name and age by scanning the table, right? So everybody understood this plan? Yes, no, in chat. This is the query is a string basically. It's a language, right? So it gets parsed into AST, and from AST, this gets generated. Now this is interesting. This particular thing. So we have this query, and this query gets translated into this. So we have got name, age, salary. So the project will have name, age, and salary, which you can reference by the number as well. Remember, in SQL, we can reference columns by number also. And we have a filter which says age should be greater than 30 and department should be engineering. Can there be more plans generated by? Yeah. Hold on. I'm going to talk about that. So uh, here is a filter clause which says, hey, the age is going to be more than 30. By the way, good question, Arjun. And the department should equal to engineering, right? And from where are you going to get these things? You're going to get these things by scanning the table employees. Clear till here? Yes, no? All right. Now it means if you understood this, it means now you are in a position to understand. Yeah, I can explain this again. Hey Rohan, nice to see you. I think you were not there in the last time, right? So Rohan is that guy who I think Anirudh is not here, right? Let me. Can somebody ping Anirudh in Discord?
I was there
Uh,
last time, but I joined
I
really
see.
late. Yeah.
Yeah, it's fine. So somebody just ping Anirudh on general channel saying that, hey, if you are available, you can join. So Rohan worked on some chips or something, which I barely understand what these guys did. But if I
We've
think
not we've not finished it,
it's fine.
obviously.
Yeah,
So
but yeah, I mean,
yeah.
the people who were interested can talk to him what he was doing. Yeah. And Rohan, we should meet. I am in Bangalore now.
Yeah.
So
Let
I'll
me know.
explain this again. Yeah, sure, sure. I'll explain this again. We have um, so we want to select name, age, and salary. So those things are kind of a project header. What you want to do? So we have got name, age, and salary. Then where do we want to select from? So this is the from clause that hey, I want to select from employees. So we have got a scan table employees that you have to scan the table which is named which is named employees, and you have to put a filter on top of that. After and that filter will be of age greater than 30, department equal to 4. Now this is the general logical plan. Okay, there are way like this whole subject itself can be a 2-hour lecture. Okay, so if you are really interested, I can share resources, how exactly logical plans and everything is generated. But this is overall how things work. Now we'll just focus on this plan for now, and we'll see what are the drawbacks and what are the things uh, which are missing. So, oops, sorry. Somebody can does a bit. Yeah. That is again a good question. So, logical plan is executed from bottom to top. Bottom to top execution. No indices on the table, right? So, yeah, we are not assuming all those things. Very simple. All right. Now, the question is how the plan will be executed. But before that, I want to talk about one thing, which is this step. So, this is a resolved logical plan. These are example of resolved logical plan. What is a unresolved logical plan? Uh, in an unresolved logical plan, or basically in a resolved logical plan, you get the right um, addresses, the right names for the table. In an unresolved logical plan, you don't know that. Oh yeah, you're right, Sambhitesh. Index scans are part of what we call physical plan. Yes. So um, in an unresolved logical plan, where to get the table from, that information is not available. Uh, so let's say if your table is in some Parquet file, which is on S3, so that address will get here in the resolved logical plan. All right. So this itself is a important step, but I'll talk about this little late. But that is what resolved logical plan is. That you get all the uh, placeholder things which is generated by the general logical planner gets resolved by the resolved logical planner, because there is one interaction which I missed, which happens in between, which happens here, and that interaction is catalog. So catalog has information that this table name exists where. Okay, so catalog has information like table name and address. Most of the time, databases or data query engines have catalog inbuilt, their internal catalog. But there are ways where you can use external catalogs as well. We'll talk about that. All right, this is going to take some time, just the design. So coming back, we have a bottom to top execution. Now, I have a question for you all. And the question is, if the employee table, if this particular table, I'll just copy this text again from ChatGPT so I can, explain a few more things. All right. It's the same thing, right? I'll just draw a pointer so that people who join late don't get confused. So now the question is, if the employee table is, let's say, 20 terabytes, then how the execution will be? If this table is huge, then what will happen? Firstly, we are saying that we have to do the scan because it's a bottom to top execution. So firstly, you'll have to load all the 20 terabytes, right? You have to scan it. Go through all 20 terabytes of file, and then you can apply filter. Doesn't seem efficient. Yes, no, in chat, did you get the problem? Because we are scanning here, we have to read everything. It is a problem, right? All right. So the problem is clear. What is the solution? People who know can drop a text. What do you think the solution is? Exactly. I didn't see you last time, I think, Mohammed Faisal. What do you do? Predicate,
Yeah,
push down.
basically, I'm
Anything-
recently working on Spark and all those things.
Oh, nice. So you are a data engineer or
Not exactly. I'm
Mhm.
basically like mostly Python and then with stuff. Recently started working on data.
nice, very cool. So what we have to do is we have to do something known as predicate push down. One first optimization / acceleration in query engine. I'll just write it here. First optimization / acceleration in query engine. Most query engine will have this by default. So you don't have to worry a lot about this, but yeah, it's there. Oh. How many of you are in Bangalore and we haven't met? I would love to meet you all. Just type in chat if you are in Bangalore so that we can plan something out. Ananya, Archit, Swaroop, Rohan is in Bangalore. In Bangalore, Akshay, we met last week. Samvitesh, where are you? Ganesh, yeah. So Ganesh
I'm
is
in
a.
Bangalore only, yeah, but
Oh yeah, Samvitesh. Then we should meet. We have never
yeah, like
met, right?
every time you have a meet, it's overlaps with something.
Yeah, I understand. So we can plan something out.
But
I would
now
love to
we're in
meet you.
Bangalore, we can meet anytime, yeah.
Yeah. So quick introduction. Ganesh is my fellow co-contributor in Data Fusion. So he came last time. didn't introduce himself. I didn't recognize him from face, and we couldn't speak a lot. So he's a great guy. Sambhitesh he was, I think, in second or third cohort, very early supporter of my work, and learned a lot of things from him. Very senior engineer, in I think he joined Microsoft, right? Or AWS.
Microsoft. I was in
Microsoft.
So
Yeah.
I
So he joined AWS. All right. So this is the first acceleration which we are going to do. That is, we are not going to scan everything, right? So I'll just ask ChatGPT to put a predicate push down for me. Got it. So this is what the first optimization is going to look like. Come on. This is what the first optimization is going to look like, which is insane. Because here, if you see, remember bottom to top execution? We have got bottom to top execution. In that case, what is going to happen first? Before scanning everything, we are filtering things out. So we are going to read only that data, what the filters wanted me to do. So the IO reduces, we read very less amount of data, we are overall faster. Instead of loading all the 20 terabytes, maybe I now need to load only 1 terabyte. Just like these are random numbers which I'm throwing out, but I hope you get the point. The filters are pushed down, and remember, push down filters need support from your storage as well. So your storage needs to support this. For example, storage like, I think I have been out of touch with the data world, but if I'm not wrong, there is storage like Delta Store. Is it Delta Store?
Delta Lake, I think. Yeah.
Delta Lake, yeah. Correct. Delta Lake. So we have things like Delta Lake, which supports push down filters, and query engines can take massive advantage of that. So this is the first optimization, first acceleration. And there are multiple, like I think S3, everybody supports this, but the most modern Delta Lake type of thing supports this. But yeah, I mean, you need support from your storage as well, not just your. Also, you need to make sure that your files are optimized. So one optimization which I'm not going to talk about because any columnar thing. So columnar is important. So all of today's discussion assume that we have assumption that the storage is going to be columnar. I'm not going to explain columnar because that will take a lot of time from the things I want to discuss. But columnar is one thing which is the assumption. So if your data store is a columnar data store, then you have really good support for a lot of optimizations like predicate push down. We have got it. It is actually it is filter push down, right? Not predicate push down. Oh no, there is one more thing, right? Projection push down, if I'm not wrong. Is there something like projection push down?
Yeah, yes.
Yeah. So there is one more thing known as projection push down. So this is how predicate push down works. There is also something known as projection push down, which I'm not going to get into because I'm going to I need to discuss something else. But this is one of the optimizations you can do. Now there is one more thing which I had spoken about here. That is, you have got a query. The query was a string. We got that query in a resolved logical plan. Logical plan looks like this. And we have got an intelligent and optimized logical plan as well. So somebody had asked, right, can't there be multiple logical plan? But you need to locate and read data in memory from the table. I need to do that, but there are efficient ways to manage things in the data store where you can just ask the data store that, hey, from this is the filter, this is the table I want. tell me exactly where, what heads in the storage I should read so that I can get only that data. So that is what your storage supports, Arunya. Right? I'm oversimplifying these things because I don't want to get into storage and all. But I just hope that you got the point. If you are more intrigued, I can share more resources. All right. So where was I? Here. So now we have got an optimized logical plan with us. That is, yeah. So somebody had asked, right? Can't we get multiple logical plans? So we can get multiple logical plan. This is one logical plan, and then this is the optimized logical plan. So both the output of both of these things are going to be the same. So a lot of times, older data query engines won't have an optimizer for logical plan, but I think Spark, Data Fusion, Velox, everybody has an optimizer which will give you most likely, which is going to give you this by default. All right. So here is something which I had spoken about. That is, we have got a catalog, which is an internal catalog, which tells where your table, where the table name and the address of the table. And the question is, a lot of times, what can happen is there can be. Um, so let's say we have an architecture, something like this. This is the query engine. Let's say Spark. Query engine talks to a data store. Let's say Delta Lake. But we have a okay. We are holding some things in memory. Holding some data in memory for supporting fast writes. Okay. All right. So there can be a possibility that when Spark talks to Delta Lake or when Spark talks to Ignite, we need to be sure that uh, we are efficiently looking for tables where they are. So Apache Ignite is going to hold some data in memory and push that data later on, let's say after 5 minutes, after 2 minutes, depending on how the configuration is, every 5 minutes to the Delta Lake. Now is Spark, and the user is oblivious to all of these things. User just has a playground from where he can fire the query. Why would you want to hold data for fast write? Isn't it done for fast reads? So that means that there is little confusion about. So what happens is if you want to do fast writes, um, it can be done only in a non-column, basically a row-like data structure. Since Delta Lake is a columnar data structure, writes in columnar data structures are slower. That is one of the reasons why we may want to hold things in Apache Ignite. So Spark is not going to write to Apache Ignite. You can have some other writer to Apache Ignite, if that makes sense. But but right now that's not a. But are you talking about flushing periodically? Yes. So here, let's say you accumulate a buffer for 5 minutes, and then you push things to Delta Lake because writing a Parquet file is expensive. It takes time, right? So don't get into that. Why are we doing this? Just assume that there is somebody who does this. Okay. So what we want to do is we want Spark to talk to a external catalog. To a external catalog. This catalog is responsible for to tell Spark intelligently, what do we need to access? Do we need to get data from Apache Ignite? Do we need to get data from Delta Lake? Right? So in this scenario, one optimization or rather one good feature to have is instead of bouncing it from the Delta Lake that, hey, I went to the Delta Lake, could not find tables there. So now I should check Apache Ignite. Or I go to Apache Ignite, check whether the table exists, and then go to Delta Lake. That hop is reduced. You just talk to the external catalog, and external catalog is always aware which tables are present in which particular database, and it can directly tell Spark, how do you plan your query. Make sense? The use of an external catalog. That is why all the databases, or all the query processing engine out there supports an ability to have an external catalog. Yes, no in chat, if everybody followed till here. One optimization was push filters and one feature is external catalog. Great. This is supported by everybody. Spark, Data Fusion, everybody. Now, the third optimization. Third optimization is going to be code gen versus SIMD, vectorization. This is interesting. However you want to write vectorization, let me just remove this and write SIMD. How many of you know what macros are? If somebody doesn't know macro, let me know. But our recent data, I see there are a lot of these problems. You are talking about the architecture. I am saying that don't focus on the architecture for now. Focus on the fact that a query engine can have an external catalog. What it can use, the query engine can use the external catalog to fetch things. For example, forget about in memory and everything. Let's say we have data stored at multiple places. We have data stored at Delta Lake. We have data stored in in Postgres, which was the older data in AWS. We have data stored in whatever S3, multiple places, right? S3, Delta Lake, which is your local. This is in-house Delta Lake and whatever Postgres, something like that. So if you have an external catalog here, which can tell Spark that this is the exact address where the table exists, that is going to just help the whole optimize the whole query processing. Instead of going to checking Delta Lake, okay, table not there. Checking S3, oh, table not there. Then going to Postgres and checking table not there. Because see, all these calls are expensive. Right? So external catalog also stores schema, which can be used for a lot of optimizations going forward. External catalog can also have information about the table. What is the number of rows in the table, stuff like that. Catalog as a metadata store, AWS, which helps in the query engine. Right. You are absolutely correct, Faisal, and I think he got it. Right. Is Sakti your correct name, or is Zoom clipping your name out? Unity catalog is another example. Federation, a classic example, right? Macros in the context of metaprogramming. Yes, C++ macros basically. Ananya doesn't know what macros is, so we'll talk a little bit about macros before getting into SIMD. So we have got two things. We have got this thing. We have got. I'll just make it to blue to show that these are optimizations which are happening. First optimization, second good feature. I won't say optimization, but a good way to reduce the overall query time. The third thing, this is fundamental. So what happens is when Spark came into the picture, Spark said that my philosophy is that programmers may not be able to write the best optimized code. All right. So programmers may need help, may not be able to write the best code possible. Right. In that case, what Spark thought was a great idea, and it was for a long period of time. Let me generate optimized code by understanding the user's code. This is known as code generation approach to query. So let's say, one very simple example. Let's say this is a Rust code which you are writing. Println hello world. So here println is a macro because you didn't because println can also take a number, it can also take a vector, it can take anything, right? So internally it creates the right function signature for you, which the final compiler can understand. So compiler does all the code generation for you. So this code generation is very common in any programming language, and that was the inspiration in Spark as well, where they said that we'll give users all a lot of macros like this. That hey, what do you want to do? You want to print something? Great. I'll figure it out what is the best way to do this. You just tell me what do you want to do. So I want to print. Now I'll figure it out what the data type is, how do you supply the right instruction to assembly, things like that. But I'll create the right function definition for you. So this gets translated into a function definition internally. Now, if this function definition is generated by your compiler. Okay. So compiler injects code in between your code. And that process is that is the resolution of macros, or that process is known as code generation. So code generation is clear, Ananya, because you were not aware of macros, so specifically asking everybody, right? So code generation should be clear. If there are questions, let me know. I'm open to discuss this more and talk more about this. So what was the problem with this, or a major limitation? CodeGen's approach, major limitation was the maintainers need to be aware / interested in supporting your hardware. Right? Because you don't have control over things. Whatever you are writing, a lot of code generation and injection is happening. So everything is not transparent. Because see, not everybody has time to get inside the JVM, see the exact bytecode, make sense out of it. That hey, if I wrote this code, this is what is being executed. So it makes debugging extremely hard. Less control on optimization. Less control / no, not a lot of manual optimization possible. Everybody clear with my hypothesis for code generation so far? Yes, no in chat. You understood what code generation is, what Spark does, and what is the problem it causes. What are the problem it causes? And one more statement, that Java is an interpreted language. All right. So yes for everything. I can explain more about drawbacks part. This is an important concept. If somebody has a problem with this, let me know. I can talk about these things later on. So the problem is, Ganesh, that once the code is generated, the code a lot of things gets inserted into your code, which you don't see because the code gets compiled into bytecode and the JVM executes it. So you don't exactly see what is being executed. So that is not a transparent thing. You cannot have manual optimizations because whatever you do, there is some macro working somewhere doing changes with your code. So you don't have complete ownership of your code. So the granular control for optimizations is just not possible with the code generation approach because compiler thinks that compiler is smarter than you, right? Or the maintainers think that you can. Code gen is not used in Spark. Code gen is how Spark works. So whatever you write in Spark, Spark internally generates a better version of the code from your code, and then that code gets executed. Your code in the original state never gets executed. A lot of things are added by the Spark compiler, and then that is the thing which gets executed. Understood, Ananya? You can
Sorry.
optimize JVM, but not assembly generated directly. I can optimize JVM. So I'm not saying that JVM is not an optimization. That optimization is JVM is not possible. That's not what I'm saying. I'm saying that it is less transparent. Not all data engineers or not all Spark developers will have time/skill to do what you're saying, Akshay. Somebody was saying something.
Sorry. So okay, when we program, we sort of program in abstractions, right? So if you write a SQL queries like start from employees, you are basically telling a program to do the optimized thing, right? Like that is the way we generally do any data query or data processing.
Yeah. So Spark code. So that is not the whole Spark program. Spark program will have a lot more things than just querying. Spark SQL or Spark query is one one of the features of Spark, right? There are many other things which Spark can do without querying. Let's say you can directly go open files, do write your own MapReduce algorithm in Spark, and never use Spark SQL. So Spark SQL side, if you keep that aside, I can totally see where it may be causing confusion, but don't. So Spark can write that kind of a code as well, right? Where there is no SQL, still you are doing a lot of operations, opening file, opening multiple files, doing your own MapReduce operation and everything. That code will have a lot more code injected/removed by the compiler, and it won't be executed in the same state what you have written. That is what I'm saying.
Got it. Thanks.
Okay. So, but it was a good thing. It was a interesting question. There was some. Did somebody say anything? So yeah, Ganesh, is the drawback part clear now? About the hardware part, if we are using JVM in this case, usually developers are hardware advanced leave the work of supporting hardware. Yeah, so that's what I'm saying. That usual cases, it is great. That is why Spark is the de facto standard now in the industry, right? So so it's similar to Java versus Rust, for example. Not everybody needs all the optimizations possible in Rust, right? But for those who need it, you need Rust to exist. JVM is limiting. Similarly, in most of the cases, Spark works great. But let's say I want to have my to Spark run on my own FPGA implementation. Now that becomes hard. Understand, Ganesh, what I'm saying? So those are the cases which Spark doesn't support out of the box. All right. So we have got code gen approach. Now I'll have more points in the end. Let me proceed a little bit, and I'll come back to this. This is how Spark worked. This is how Spark worked. So we have got another thread which says that hey, hardware today is natively SIMD. So instead of enforcing code generation approach, why don't you enforce vectorization as a first principle? Instead of injecting, doing code generation and everything, let's make the data structure parallel. Let's make all the execution natively parallel by default. So the change in the mindset is Spark is over concerned about making things correct in the distributed setting. Data fusion, which you can see as a new thing in the big data industry, getting really popular, being used by multiple companies. Data fusion's primary objective is that I want to make things faster on a single node. I am not interested in making things correct in a distributed setting. That is why there is a clear code gen approach and there is a clear SIMD based approach. Remember the last time I had mentioned, in the olden days of distributed systems, people paid no attention that every node can have a personality. Nodes were just assumed to be homogeneous, right? We have 5 nodes. But all the 5 nodes may have different RAM, different chip support, different bandwidth support. I don't know. So rarely we have got homogeneous hardware in our setting. Most of the people have heterogeneous hardware type of a thing. So in that case, how are you going to work? How am I able to, prioritize stuff, do things like that? So those things are not out of the box possible in older implementation of distributed system, and one of that limitation is with Spark. Obviously, you can have a clear that this is going to be mastered, this is going to be pool of workers, things like that. But yeah, I mean, the control is little less. It is not natively SIMD optimized. Here, Data Fusion says that hey, every hardware has got a SIMD register. So I need to optimize. I need to look my nodes from that angle. That I am going to natively support vectorization. My data structure is going to be Apache Arrow, which is a columnar data structure. I am going to be columnar throughout, right? That native SIMD support is going to be there. So you have got one of the benefits of this is lesser RAM usage, less RAM usage, more control on execution. Mostly what you write is what get executed. Why I'm saying mostly because Rust changes a few things as a language, but as a framework, Data Fusion executes exactly what you have written. You have got more control. You can write inline assembly as well. So very easy to support your own FPGA / whatever accelerator. There is no change. Query looks exactly the same. That is the beauty. All of these things are internal. So for you, there is no change as a user. I mean, query is going to be the same. Select star from table. Right? Now, the question is, this is one approach working well for the last 10 years and has become de facto. There's another approach who got the same level of respect in Apache community. So basically, Apache community has got a top level project tag. So Spark had it in 2014, and it took 10 years for Spark to become an industry de facto. Data Fusion got the same tag, top level project, last year, 2024. A lot of the companies are using Data Fusion to extend things out because Data Fusion is just a query processing engine, extremely optimizable. So we have got these two approach. Andy Pavlo, who is a CMU database professor guy, very yeah. If you are into databases, that is the lecture you should see. And we will talk more about CodeGen versus SIMD in the next session, where we will talk about what is happening in the world of modern databases. But yeah, he says that it is empirical that uh, uh, the SIMD based data processing engines are performing better, but there is no benchmark right now which can be a clear differentiator that code generation approach always performs bad. So Spark as an engine, the whole engine can perform less efficiently as compared to data fusion, because these things are way more than just CodeGen versus SIMD. But for example, if I'm not wrong, I think DuckDB is CodeGen. DuckDB is also a modern data engine. It uses CodeGen approach, whereas data fusion uses SIMD. Performance of both are extremely close. So sometimes data fusion wins, sometimes DuckDB wins, right? So there is no clear winner here, but there is this one thing which we should keep in mind when designing or thinking about accelerating a query processing engine. Because if we want to accelerate things on our own hardware, because of the native SIMD support in data fusion or any query processing engine which is SIMD based, you get to optimize things very easily because things natively support in parallel data structure out of the box, whereas Spark does not have that support. So accelerating Spark becomes a harder problem. We'll see in the coming forward that how SIMD approach is being used to accelerate code gen approach. So the native code gen stack is getting support from SIMD, and we have a project named as Data Fusion Comet. Okay. So we'll talk about that as well. Now, so is it clear till here? Do you have basic understanding of the difference in both of these worlds, CodeGen versus SIMD? Yes, no in chat. That there are two school of thoughts. Uh, Problems with one school of thought, problems with another school of thought. No clear winner here, but it looks as if people prefer SIMD approach more in modern world. That's it. All right. So we have got three things. I'll just create a blue box here. SIMD, external catalog, predicate pushdown. Now we are in a great spot. If you have already used data fusion models where SIMD is used. So data fusion natively is built on top of Apache Arrow. Apache Arrow is a in-memory columnar data structure. So natively SIMD, any operation is going to be in parallel. So where was I? Yeah, so we are in a great spot to talk about talk about acceleration, because there are two aspects. One was the logical plan step. We have seen what. All right, so let me talk about a little more here. So we have seen what logical plan is. Now comes physical plan. So I'll ask quickly ChatGPT to generate physical plan for me, so I can show you physical plan for this query. All right. So this is the example I'll just write it down here, okay? Because now we are going to focus on the physical plan. So now we have got physical plan. This is how the physical plan looks like. Very similar to logical plan, few changes. Project remains the same. The things we want as an output. Filter exactly tells you what we want to do. We want to filter. Here are the changes. How exactly it is going to execute on the hardware. So it is going to use HDFL file scan, assuming you are built on top of an HDFL. So HDFL is Hadoop file system. If you have a Hadoop file system, you are going to do an HDFS file scan for employee table. Here are the push filters, and here is how the schema is going to be read. I think this is predicate push down, if projection push down, if I'm not wrong. But yeah, I can be wrong here. I have forgotten a little bit about how exactly physical plans work. But main thing is, if you can see here, we have got the exact instruction which we can give to the executor how exactly you want to run this code physically. The logical plan is all about planning the query. It is more concerned with the query, that hey, how I can optimize the query. And it has general functions like scan, but it doesn't tell you how exactly you're going to do the scan. This physical plan is going to tell you exactly that how the scan should happen. All right. So it's going to tell you that, hey, you have to go to the HDF. We are using HDFL file system, HDFS file system. So you have to go and you have to do a scan like this. Okay. So these are like this is how physical plans work. Now the question is, what are the optimizations which are possible? We are talking about accelerating things, right? So one thing which is critical and which is about acceleration is that since we have a code gen versus SIMD approach, what we can do is when we have a physical plan, I'll maybe just post again another here. So when we have a physical plan, what we can do is we can ask some software to rewrite this plan for me. Rewrite and convert this to use modern SIMD registers in my CPU. This is just an idea. There is a physical plan which is generated. We are not going to talk about how it is generated because we are more concerned with the optimizations and accelerations. So there is a physical plan. We have to rewrite that physical plan in such a way that it can be executed on the modern hardware using SIMD registers, because that support is not available but in vanilla Spark. Is the idea clear? Do you understand from the idea perspective what we want to do? Spark is oblivious to SIMD and everything. Can we take Spark's physical plan, because we rely that Spark can generate good physical plans? So, and that is the final output of a query engine. So we take the physical plan and we rewrite that physical plan such a way somehow that it will be executed on the modern CPU using SIMD registers and everything. Okay. Any no's here? Everybody following? All right. The question is, how do you do it? So the project which does this is Data Fusion Comet. Another optimization. Is it the only optimization possible? No. There are more optimizations available. But one of the optimization is this. So if you want to rewrite and convert this to use modern SIMD registers in CPUs, then Data Fusion Comet is a good project. If you want to rewrite, pay attention. If you want to rewrite this and convert this to use GPUs, same physical plan, but can we convert this to use GPUs? Yes, we can. And the project is NVIDIA Rapids. Both of these projects were led by / founded by Andy Grove. All right. So we'll now see what happens. Like, how do you convert? Is that what we are going to see? But more than that, this is the idea. So what happens is there is a package which you can plug in, which you can create by compiling Data Fusion, Comet, and NVIDIA Rapids. You can supply that as a jar when you're running your Spark cluster. And on the commodity hardware, that is your same stack, whatever you are using right now, without changing anything. On the same stack, you can get up to 2x. No, up to is more than that, but minimum 2x performance improvement. Remember, we are not changing anything in the front end of things. All of these things are happening, so we as a system programmer have to pay attention here. The user program doesn't change at all. So your data engineers, your Spark developers are still writing Spark as if nothing has changed. But we are doing all this drama here to accelerate things for them. So we are going to give them at least 2x performance improvement. Or what does it mean in terms of business sense? 50% reduction in cost. If performance improvement is twice, then you can do more things, right? So you can get up to 50% reduction in cost. So it's a good project. It's not just an academic thing. And similarly, if you have GPUs, you can get more performance than this, but you have some restrictions on how the performance will be achieved. So let's see how exactly this conversion happens. Oh, by the way, this project is in Rust. This is CPP because of CUDA. CUDA itself is a low-level programming language, and I have a brilliant talk. YouTube. The CUDA is a low-level programming language. It's a brilliant talk. That's why I'm spending time to search that. CUDA programming language. Yeah, this one. Insane explanation as well. Then again, chat, somebody drop it in resources. Awesome. So it is because of CUDA. Now we have to understand how this conversion happens. So what happens is we have got physical plan, and physical plans are also executed bottom to top. Hence, you can think of it as a post order, forget about post order, as a DFS, depth first search type of execution, which means what? It means that physical plans can be, I'll tell you, physical plans can be represented as an AST. Quickly, yes, no in chat if you agree with me on this. Meanwhile, I'll take this question. How Data Fusion differs from Data Fusion Comet? Since Data Fusion is already a query engine, alternate was, yeah, you're right. I'll tell you what Data Fusion Comet project is. Then that will make things clear. Everybody in agreement with me here? A physical plan, it is bottom to top execution. So you can represent it as a tree, right? Fast to use SIMD register. Or is it SIMS register? Is it something else? What is SIMS register?
No, I typed it wrong.
Oh.
They are ASTs, right? Because they have to map to the CPU. So you need to represent it with an AST.
Correct. So for now, we'll assume that the physical plan looks something like this. Okay. So this is your physical plan. Now, conversion. Conversion is actually very simple. What we do is physical plan actually like can never be extremely long. So you can iterate through the physical plan. Iterate through it, which means O ON, number of nodes or the depth. You have to iterate through it. So you have to iterate through physical plan and do a node by node translation. Just let me know if you have already understood the idea. And then you get final physical plan, which will be like this. Give me some time, taking time deliberately. Deliberately taking time here so that your mental map is clear. All right. So what we do is we iterate node by node and see if the similar or the compatible node is available in Data Fusion slash Rapids, depending on where you are accelerating, which means the GPU kernel is available. Kernel supports this. See, not every node can be supported by Data Fusion because those are two different software. For example, there is one project which I worked on, very simple one, where there was date conversion. Okay, so you write, you want to convert that date into datetime format. The problem with Spark is Spark supports, I think, even if you write 25, oh sorry, if you write 3-digit year, Spark can convert 3-digit year, 4-digit year, 5-digit year, up to 8-9-digit years. Data Fusion supports only 4-digit years, right? Everybody understood the difference? How casting of a date casting from string to date is a different thing in Data Fusion and Spark. In Spark, you can cast even a 3-digit date, 3-digit year to a proper year format in Spark. So it supports 999 year. But Data Fusion requires even the string to be at least 4-digit so that casting can happen properly in a datetime format. So is the difference clear between these two? That both are the query processing engine, but then the casting operation is different between these two. Yes, no in chat. All right. So because of those small difference, not the whole physical plan can never be translated. So what we do is we identify at least the most expensive nodes. We try to write it in Data Fusion. We try to write that in as a GPU kernel. So for example, filter operation or the sum operation can be a kernel. multiplication operation can be a kernel, multiple things like that. Whatever can be accelerated on top of GPU. You can go through NVIDIA Rapids and see what operations are where exactly the acceleration is possible. All the queries and examples are there. Similarly, you can go into Data Fusion Comet. Data Fusion Comet is little more generalized than Rapids because the hardware difference is not there. Whatever can work on one CPU in a JVM setting can work on in Data Fusion and Rust setting. It's just that there are some fundamental differences between these two libraries. Spark has a different take on things. Data Fusion has a different take on things. That is why same plan cannot be executed. So you have to translate this plan, convert this plan by iterating through the plan, seeing which nodes can be converted, right? If the nodes can be converted, you create a new plan, which is this. And the new plan, the nodes which can be converted will be executed by Data Fusion. Else, it will be fallen back to your Spark. So usually what happens is either the whole plan is good enough to be executed in Data Fusion, or the whole plan is not good enough to be executed by the native Data Fusion executor. So it falls back to the native Spark execution. Node by node execution doesn't happen. So let's say there are 75% of the nodes which can be benefited by the acceleration. We will execute the whole plan into Data Fusion. Make sense? So we will have these green things will be Data Fusion nodes, and the rest of these things in yellow will not be Spark nodes, but will be Comet, Data Fusion Comet nodes. Data Fusion Comet nodes. Now, what is a Data Fusion Comet node? It is the bridge. So we know that Data Fusion doesn't support 3-digit years. Spark supports 3-digit year. So we, as a project, created a specialized node which will say that, hey, if the plan is going to be executed in Data Fusion executor, let me handle this inside Rust like this. Because one node cannot be executed in JVM, one node cannot be executed in Rust, right? The whole thing will either be executed in Rust, the whole thing can either be executed in JVM. So we, through the JNI, that is how you talk to two different programming languages in the same process. So you take the physical plan through JNI, translate it. If the plan seems to be fit for execution, you see if it can be executed or not, and then you execute it, and then you take the result and give the result back to Spark through the same JNI interface, and then Spark can do the job later on. So this thing causes a lot of acceleration. So somebody had asked that how Data Fusion differs from Data Fusion Comet. So this is the Data Fusion and Data Fusion Comet difference. Data Fusion Comet uses Data Fusion to accelerate Spark, but on top of that, it has a lot more, sugar, you can say, which are things like the support between casting of timestamp / date time between Spark and Data Fusion, and all these type of bridges are there in Data Fusion Comet, which allows your query to execute without fail, even in the Data Fusion environment, right? So Data Fusion takes things closer to the metal. So whole thing is faster. We know, right, why Rust is faster than JVM. So that is a clear win there by default. But even after that, there are a lot more optimizations which are baked in Data Fusion as well as Data Fusion Comet, which makes the Spark native execution faster. So that is one Data Fusion project. And similar to that, we have a Rapids project. So whatever can be executed by the GPU will be executed by the GPU, and you will have some specialized nodes to act as a bridge. And that is how accelerators are written. So this is the basic idea how accelerators are written for Apache Spark / any query engine. So Data Fusion is a generic. Data Fusion is a data processing engine. It's not an accelerator. Comet is the accelerator, which takes the Spark plan, accelerates it using Data Fusion. Is it clear, Akshay? I'll write it here just to avoid confusion. Comet is the accelerator. it takes physical plan from Spark and it accelerates that using data fusion. Now, data fusion and Spark are not completely compatible. So Comet has implemented a lot of bridge. Spark is a similar vectorized version which is available in managed. Yeah. See, so but Photon is not open source. So you have to pay to Databricks.
Yeah.
Comet is an open source accelerator.
Totally.
Right? That is why I was super excited by Comet project. You're absolutely right. And we have taken a lot of inspiration from Photon as well as Velox. Velox is also a C++, if I'm not wrong, SIMD based
Right.
framework written by Facebook. Right?
Yes.
And that is what makes the whole Comet project so important for in general for the world, because Databricks has also understood very clearly that Spark or the older query processor needs vectorization version to be accelerated or managed properly, so the cost can be brought down, everybody is profitable, things like that. So that is why Andy Pablo said that world is moving towards vectorized version, but still there is not an academic argument which I can make right now which can clearly say that this is obviously why vectorization makes sense, because there are very highly optimized code gen approach also available who compete very heavily with vectorized engine. So vectorization in itself is not that powerful. It gives you a lot of control, a lot of power which you can extrapolate on, but just being vectorization is not enough. That is what I wanted to say. But thank you for sharing this. So everybody understood this so far. What does acceleration mean? What is Data Fusion Comet project? What is NVIDIA Rapid project? Like how they do the acceleration? Is that clear? Yes, no in chat.
Yeah, how a system decides to execute completely in Spark or completely in Data Fusion Comet, if like partial nodes are Comet or partial nodes are Spark based?
Correct. So during this translation, there is if important nodes, let's say you have got shuffle has joined, right? So if shuffle has joined can be replaced with the data fusion implementation of shuffle has joined, and we have got the remaining nodes have the Comet based implementation. As I gave you an example, right? That casting is different. So for that, we have got Comet operators, which are nothing but wrappers on top of data fusion. So if that enough as in if 100% nodes can be translated in either Comet operators or data fusion native operators, then we execute the plan. If that is not there, if even a single node is there, which the implementation is not present in either Comet or in data fusion, then we tell Spark that hey, this cannot be executed in our executor. You have to execute it on your own.
Yeah, got it. So it should be like 100% compatible.
100%.
Yeah, okay.
Correct. This is wrong. All right. 100% compatibility. 100% compatibility. Compatibility. Oh, whatever the spelling. Compatibility. All right. So that is all I want to talk about today. That is, we started with so MapReduce is essentially how everything, hold like these things. So after physical plan, MapReduce comes into the picture. So we started with a query, which is very simple. We came up with a logical plan, which is again very simple. From this logical plan, we learned that how exactly a logical plan can be optimized and accelerated. That is various things like predicate pushdown, external catalog, stuff like that. Then we also went and understood that there are two modern as in most famous query processing engine in today's world, which are just query processing engine. That is Spark and Data Fusion. So both are by the same organization, that is Apache Foundation. So you have got one which is in CodeGen approach, one which is in SIMD approach. CodeGen approach, we understood what is CodeGen, what are the problems it can have. Problems as in shortcomings, not optimizations possible. Those are also correct. It's just that not optimizable. What are the things which are there in SIMD? What are the benefits of being in SIMD? Data Fusion uses SIMD by default. Somebody added really well that Photon is Photon is the engine which Databricks uses itself. So world is definitely moving towards SIMD. However, whatever the take is by Andy Pavlo, I gave it that to you all as well. Then we learned how a physical plan looks like. We understood what physical plan is. I'll talk about a Tiger Beetle at ClickHouse, what physical plan is. And then we learned what is the meaning of rewriting a physical plan into SIMD thing or into GPU thing. So we formulated what is the meaning of acceleration. Then we realized how acceleration happens. Then we saw two projects with which we can do the acceleration. That is Data Fusion Comet and NVIDIA Rapids. Data Fusion Comet for a CPU-based execution, Rapids for a GPU-based execution. And we also saw the process, how exactly the translation happens. We also saw why do you need another project like Comet, because of the compatibility issue. So Data Fusion has got its own take. Spark has got its own take. We want to build wrappers on top of Data Fusion so that we can be compatible with Spark, and that is why we can execute the whole plan in native Rust and not in the JVM, so that we can leverage everything. So we are faster. That is what we understood. And finally, we were able to formulate and understand that several ways exist to optimize, accelerate your query processing engine. We saw a few famous ones. From a systems database engineer's perspective, all of these things change and nothing in the front end. So you can do all of these things, and your data scientists, your data engineers will never realize that things are changing in the back end. Their code will run in the exact same way. So that is the beauty of it. That was the core idea which I wanted to talk about. I hope it was fun and interesting. Does Tiger Beetle and ClickHouse like modern database? Yeah, Tiger Beetle is also native SIMD, but you have to realize Tiger Beetle and ClickHouse are very different. That's a good question, Akshay. I'll come back to that. Tiger Beetle is mostly a write-only operation. So it's a OLTP type of a database. ClickHouse is a OLAP database. I have not seen architecture of ClickHouse, so I don't remember anything about ClickHouse. But ClickHouse is written in C++, so I think it's vectorized. Yeah, that was going to be my guess, but great that you were able to find it. So thank you. Tiger Beetle is a different database, so it's not a query processing engine. ClickHouse is a query processing engine. Okay, it's a OLAP database. ClickHouse. Does Data Fusion support FPGA or only commodity hardware? There is no restriction. That is the beauty of Data Fusion. Highly extensible software. So you can take Data Fusion, you can have your own FPGA implementation, just extend Data Fusion. So why I'm telling you in this way is not that I'm overhyping Data Fusion. The goal is composable data stack by, what was his name?
Wes McKinsey, I think.
Wes McKinsey. We can talk about that sometime later, not today. Maybe I'll talk about this when we discuss modern databases in next session. To see what is the modern hypothesis, the modern manifesto, how it is different from the monolith databases before. Just read through this. This is a blog. It's not a paper, so very easy to read. and you will get a lot of pre-reading materials as well for the next session, and you will understand your question. Like my answer basically, Akshay, that why did I say the data fusion supports FPGA, although there is no native support, but it can be extended. Okay. Open source Spark have open source Spark have Tungsten engine to do some optimization, but still certain. Yeah, that is correct. All right, I don't have anything else to add in this topic of acceleration, so I'll just stop here. All right, guys. I'll stop the recording to keep things shorter, and then we can, discuss more if people are interested. Stop recording.